Galvanic cells, also called voltaic cells, are redox reactions that have been separated so that we can trap the electrons in a wire so that we can use them to do electrical work. In this example, we'll consider a reaction between copper and copper 2 ions and zinc metal. Some books use a special kind of notation to denote the type of electrical cell that's going on. Basically, we'll draw a symbol to represent the contents of the beakers in the galvanic cell. So let's say we have a large beaker with zinc metal in it. Zinc metal is kind of gray, so I'm going to draw it as a thick bar. The solution that this zinc metal is in is going to be zinc ions and then some kind of inert counter ion like sulfate. These will be around to balance charges, but not to do much else. Okay, so we have a zinc plate and we have zinc solution. What we would do is we would write that symbol as zinc metal as a solid is in a solution with zinc ions. And then we would describe the other half. In another container, we would have our copper metal, which I'll draw as an orange bar. We all know it's a little bit more copper colored in real life. That's as good as I've got today. And so we'll label this copper metal, and then copper ions in solution. For our electrical chemical cells to work properly, you would want to choose a counter ion that was the same so that we know it wouldn't react with either ion. Okay, so then I could write that my copper 2+ ions are in the same beaker as my copper metal. Okay, so we have two different ways of representing this reaction. We have the net ionic equation, and we have this new symbol form called a cell diagram. Okay, now these two beakers won't be able to react with each other if there's no way for the electrons to transfer from one place to another. So the first thing that we need to do is build something called a salt bridge. The salt bridge can essentially be any kind of tubing or even a paper towel that's saturated. But if it's a tubing, it would have two little cotton balls. Then you would fill one end of the tube with something inert like sodium sulfate. With these ions in here that won't react with zinc or copper. And then that way it will allow for movement of charges, which conducts electricity between the beakers without affecting the copper or the zinc. The last step would be to connect our two electrodes, the metal pieces, with a wire. Usually we use copper wires for these, which are the insides of alligator clips. Okay, so now let's take a closer look at different spots on our galvanic cells. To do that, let's number all of the important pieces. Let's look at what's happening at the zinc electrode, what's happening inside of the wire, what's happening at the copper electrode, and lastly, but definitely very interestingly, what's happening in the salt bridge. according to my chemical reaction, my zinc metal is going to be turning into zinc ions. So where do those electrons go that we would usually just write in a balanced half reaction? Well, if we zoom in on what that zinc plate looks like, we can envision a whole bunch of zinc atoms near each other. Also in solution are zinc atoms that have lost a few electrons. We can model those as smaller dots. Okay, so when zinc loses its electrons, where do they go? They go up the wire. So let's say this little zinc has 2 electrons. If we zoom in very, very far, we can see from a model what would happen to the size of the zinc. Electrons make up most of the space in an atom. So if I had 2 electrons on the outside and those suckers decided to leave to balance a difference in potential, my size of my atom would decrease. That would mean that my pieces of my metal would jump into solution. So as the reaction proceeds, the zinc electrode is going to lose mass. We can also remember that the zinc is the atom that's being oxidized. My AP chemistry teacher in high school used to help me remember whether this was called the anode or the cathode with a little memory trick. She said that we could remember it by picturing an ox. So I used to visualize an actual cow with little cow ears and a fun face. Okay, so we would call the zinc electrode the anode. This is where the oxidation is occurring and where the electrode is losing mass. You need to remember all of those pieces. Okay, now let's consider what's happening in the wire. I like to consider all of the wires in my life to be made out of copper because it's really, really conductive. So I envision our wire as having a bunch of copper atoms all lined up. Okay, so if I have some electrons that are being passed through the wire, what they're really doing is kind of bumping their way from one atom to another. Now, it would take a while to draw all of these valence electrons, so I'm going to pause for a second. Okay, now I want you to envision why the electrons leaving the zinc anode and traveling through the wire. All they have to do is be passed from atom to atom to atom in a conductive material like the copper. It's important to know that the electrons travel from the anode, where the oxidation is happening, to the other species, to where the cathode is. In this case, that's going from the zinc towards where the copper's at. So our electron flow would be to the right. That means that my current is going to flow to the left. If you remember from physics land, current is defined as where the positive change is happening or where the positive charges are traveling. But that was before they knew that current was produced by the movement of electrons. So just run with it. Electrons travel from anode to cathode, and current travels from cathode to anode. At the copper electrode, we have almost the exact opposite of what's happening at the zinc electrode. I like to visualize my coppers as a bunch of individual atoms. kind of like my model of the wire drawing. Okay, so envision that these electrons are traveling through the wire and they're landing themselves near these copper atoms. Now, each individual copper only has 2 valence electrons. And as those extra electrons are arriving, they're going to need to go somewhere. Also in solution, we have a whole bunch of copper 2+ ions. Those 2 pluses are going to attract the electrons to themselves. And let's draw 2 arrows for 2 electrons for the copper 2+, and those copper 2s will become copper metal atoms, gaining size because of the extra electron density and changing colors. So we need to remember that the copper electrode, called the cathode, is the electrode that gains mass. And it's important to remember that this is where our ions are turning into solids, which causes that change of mass. Okay, it's also really important to remember that this is the reduction. My AP Chem teacher in high school helped us remember which electrode was cathode by calling it a red cat. So I envisioned a tiny little cat with pointy ears and cool little feet and a really neat tail and some eyeballs and a nose and a smile. That's my cat. So my red cat helps me remember that the reduction happens at the cathode. I remember that reductions mean they're gaining electrons, which means we're going from ions to solid, and when you're adding solid somewhere, it gains mass. The last piece of the galvanic cell, or the voltaic cell, to consider is the salt bridge. I'm going to draw a giant tube. In the salt bridge, at least the one that I made up, I put a bunch of sodium ions and sulfate ions. Okay, now these ions are there to help balance charge. If we remember correctly, the copper 2s that we were just talking about are going away and they're turning into copper solids. That means that our beaker on the right-hand side is losing positive charge. That's going to attract my sodiums in my salt bridge over to that area that now has a positive deficiency. In fact, that beaker would have too many sulfates left over. Okay, so now we have to think about the other beaker. In that beaker, we had zinc metals becoming zinc 2+, with an overabundance of 2+ floating around that beaker. That would attract our sulfates to go towards those new positive charges to balance them out. So those 2 minuses will balance out the 2 pluses. And that's everything you need to know about how galvanic cells work. And then